Good morning or good afternoon, depending on where you are in the world. Today we're going to look at the chapter parallelization of the singular value decomposition. Now, where are we coming from? Basically, we've got two software refactoring projects, these being a finite element software tool for structural mechanics and dynamics, and the other being a data filtering software tool for airborne survey analysis. The former is an exercise in the solution of partial or ordinary differential equations in space and time, where there are large-scale implicit or explicit nonlinear equations, and the latter is an exercise in space-time filtering of data. Both are dominated by linear algebra operations in real or specifically floating point number space. What we wanted was guidelines on how best to use CHIUW for the tasks mentioned, and we considered examining various learning experiences from which to create those guidelines. We ignored dense linear equation solution as too trivial. We also ignored dense eigenanalysis as too complex, and similarly we avoided sparse linear algebra because it was complex too. We chose dense singular value decomposition, SVD, that we already used in at least two applications, formulating individual finite element matrix factors that were written in Fortran, and the other which was airborne data sampling, filtering and reduction, which was written in C++, which was itself a translation from code that was written in Fortran. We deliberately upscale the size of the problem in F for performance testing. The classical SVD, as published by Golub and Reinsch in 1972 in Algol 60, decomposes an M by N matrix into a triple matrix product. It's been the basis of many clones, including implementations in the LinPack software toolkit and numerical recipes in C. It's both computationally intensive and mathematically complex, and it was deemed the best candidate for this exercise. We want to learn how best to use CHIUW, not how to write a better SVD. This is an exercise in creating parallelization and programming guidelines. Newer, better algorithms were ignored because they brought nothing extra to the table. So, guidelines for the exploitation of CHIUW's parallel and generic programming features are wanted. Accuracy and readability weren't going to be sacrificed for performance, but by the same token, performance should be competitive with Fortran, whatever, or C++, whatever. And mathematics, not programming, was assumed to be going to dominate the parallelization and implementation. So what CHIUW features were we likely to find useful? The main one was going to be the for all for data parallelism. We didn't expect that we were going to be doing task parallelism. We were certainly going to exploit generic programming because we wanted to make sure that the code supported both real 32 and real 64 operations without change and knowing what the type was. We were going to use array operations, including data handling, such as slicing, and mathematical operations on chunks of arrays, or whole arrays as it might be. And we were going to use CHIUW's default array storage scheme, which was row major storage. The last of these has major implications in terms of needing to program the mathematics to avoid cache misses and specifically to ensure cache hits. And because Fortran uses column major storage, which is obviously different, the refactorization of old Fortran code is not just going to be a transliteration of those programs. Looking a little bit more precisely at that mathematics, given an M by N real matrix A, its SVD is a decomposition such that A is factored into U times W times V transpose, where W is the diagonal matrix. It's got the singular values WI along the diagonal, and both U and V are orthogonal with respect to themselves. 3 tasks make up the Goldman-Reich algorithm. The first is a bidiagonalization of A using household reflections to form, say, W dash. Second is an accumulation of those reflections to form an estimate of U and V. And the third is an iterative diagonalization of W dash using a shifted QR strategy to form W. And operations performed on W dash in that QR strategy are also applied to the estimates of U and V. Those 2 operations, the bidiagonalization and accumulation, comprise the following algebra. First is an outer product, and the second 2 are just matrix multiplications, the first by a matrix and the second by its transpose. And while the final diagonalization is multiple pairs of sets of Gibbons rotations. By pairs, I mean you're working with both U and V. The first set is through angles theta I, and each is applied to a pair of consecutive columns of the estimates of U and can be written as a Gibbons rotation matrix applied on the right to U, or to 2 columns of U, an M by 2 matrix. And that 2-column matrix on the left-hand side is problematic because it causes case misses with Chappell's row major ordering. So the Gibbons rotation operation is case hostile and involves small matrices. The algorithm needs to be made case friendly and involve preferably a single matrix. Mathematics of the Gibbons rotation done on columns of the estimate of U can actually be written in complex space by constructing a complex vector from those 2 columns. The first vector is used as the first column is used as the real component of that vector, and the second column is used as the imaginary component of that vector. And it's multiplied on the right by a single complex number, where that complex number is simply cos theta I plus I times sine theta I. And a similar formula exists for rotations done on columns of the estimate of V. Now, the QR strategy is needed for each singular value. Each singular value needs some unknown of number of QR iterations. At each such iteration within the Chappell implementation, the Gibbons rotations are applied recursively to pairs of columns across some JK slice of the estimate U, which is a bigger matrix than just 1 or 2 columns. Each of those complex numbers, GC theta I, that's associated with an iteration is captured in, say, some array whose base type will be complex 2W, remembering that A has a base type of real W. And similarly for the Gibbons rotations applied to the JK slice of the estimate V. For a quick explanation of how that slice is deduced, have a look at the paper. For a more detailed explanation, please read the original reference. And when it comes to implementations, all operations were mandated to access array data across the row, and that was the best way to achieve data locality in a row major storage scheme. And some Chappell code snippets will show what was used in the basic operations, and they assumed that ZD is the domain of Z, XD is the domain of X, and YD is the domain of Y. Vector outer product. This can be parallelized with a single line of Chappell. No loop unrolling was attempted, and Chappell does a great job of optimizing this. Matrix vector product, nothing special here. The only thing is that our routine inner, as we implemented, is a naive inner product with a 4-way unrolled internal loop, and its second 2 parameters are mandated to be 1D arrays with unit stride. The second matrix vector product involving the transpose of the matrix cannot be parallelized like the previous matrix vector product without some serious case misses. And obviously that gave us some really big performance problems. So instead we parallelize it with the pseudo partial reduction in Chapel, which again is really a one-liner. No loop unrolling was done here. And certainly since 1.2.2.0, the performance of the above has been excellent. We did have some problems with some earlier versions of the compiler. I mean, stuff before 1.18 was really awful. Now, the contribution to science, I suppose, that our paper's got is that it implements the Gibbons rotation within the QR strategy using that complex breakdown. It can be written naively in the same way as the original reference code, where we're looking at implementing those formulas that we just discussed with a nested pair of for loops. If you look at that, you'll realize that it can't be parallelized as it stands, and it causes major cache misses. But by inverting the order of the loops, we can rewrite this again with nested for loops, but the insides of the outer loop are now operations being done on individual rows, and those operations on the rows are themselves independent from other rows. In practice, we actually don't use complex numbers and the associated complex arithmetic. We just do it all longhand. And that's largely a function of the compilers and C, because all of those operations tend to be done using functions. In C style compilers, in Fortran, complex arithmetic tends to be done in line. So, interesting. The rows themselves are processed in tiles that are unrolled 4 rows deep for performance. And if you look at this hard, the algorithm accesses data across the rows, so it's very cache friendly. We did some performance testing, even though this exercise isn't about performance, it's about those guidelines. We deliberately took test case matrix 3 from the original Goldman range because we wanted to make sure we were comparing apples with apples. We had 3 test cases, 2400 by 2400, 3200 by 3200, and 4000 by 4000. And you end up with a rather conventional looking performance curve for parallelism and speed up. The performance with Fortran. When we compared the serial performance of Chapel using a 1603 by 1603 test case with a linpack version of the original algorithm, we saw that Chapel was marginally faster than the Fortran. Interestingly, when the matrix dimensions were a multiple of 2, Fortran was slightly faster. A statistic we assumed, but we didn't really verify, was a speed gain coming from the vectorization that was done in the Fortran code. So what did we achieve? Well, we critically examined what we did in the implementation, and we used that to create some very clear and simple guidelines. We now have a parallelized SVD implementation in Chapel that works well. It's performant and comparable to Fortran. The Chapel code is quite readable. It's as accurate as the original because we weren't trying to do anything more spectacular. Chapel's ease of expression made the implementation straightforward. We could certainly use some improved numerical techniques, especially when it comes to the householder reflections, to yield a better SVD algorithm. Similarly, we could use improved algorithms to yield an even better and faster SVD, but that really wasn't what we were aiming at. Vectorization, when it arrives in Chapel, should certainly improve performance. Please read the paper for more details, and many thanks to those who assisted with this work. Thank you very much for listening.